Welcome in. All right, so I have a few examples here, so you can look at the timelines as well. If you can jump over to whichever question you want. So there's about 6 questions, although I'll cover the first 2 kind of simultaneously. So in the first question, okay, this is related towards work, okay, and some examples for work. So it says, give 2 examples of where a force is applied, but no work is done. Okay, so that's the kind of first question that they ask us. So there's might be some force, it's applied, but yet we have no work, at least no mechanical work that's done. The second question asks, give 2 examples of where a displacement takes place, but again, no work is being done. All right, so those are the 2 instances. Okay, so if I cover, let me cover the first one first. Let's make it very simple. So work is related towards indeed, so the force which is going to be applied, and then whatever displacement which is caused by that particular force. So, when can you apply a force and then there's no work? Well, you can think about applying a force, but maybe there's no displacement. Now, when can that happen? Well, one example could be, if you take and something is maybe extremely heavy or it's extremely sturdy, and you're trying to apply a particular force in here, and it just doesn't move. Okay, so within here, maybe you're not strong enough to move it at all. It has so much friction opposing you that it just simply doesn't move. So the displacement in here would have been 0. So it doesn't matter how much force you're going to be applying. If the displacement is 0, like pushing on something, like a wall, for example, it's not going to really move. Well, then the work done on this particular object would actually be 0. So that's one example. Now, another example is, if you're applying a force, we can kind of take something similar, but in this case, I'm going to tie it into the second question. So within here, let me kind of remove this out. And let's relate this back to, if you recall what the definition of work, I'm going to just write work is equal to, so it is the force vector, right? It is being multiplied, so the magnitude of the displacement, and then you have the cos of the angle in between these two. Well, so I just gave you an example where this was 0. Okay, so that's one case, so definitely there'll be no work. Now, let's think of an example where maybe this is 0, right? So when does cos theta equal 0? Well, when these 2 vectors are at 90 degrees to each other. So when the force and the displacement are at 90 degrees. Well, when can that happen? Well, so for instance, if you're going to be carrying this box, okay, so let's say you're moving in this direction, so you're going to be covering some kind of a displacement. So that's checked in. However, the force, that you're applying to hold this box up, so it doesn't move, at least this is with respect to the horizontal, so to the kind of x-axis, not to the y-axis. But you're going to be holding this, obviously you're going to be applying a force upward. So in this case, to try to hold this up, this particular weight, but you are moving, horizontally. So with respect to the horizontal, there's actually no work being done. So within here, so that's something that you might do. Now, you can also apply the same analogy to that second case, right? So right here. So for example, there is a displacement, yet, there is no work being done. Well, this example is going to capture both of these, meaning, you can take a force and no work is being done because the angle between them is 90 degrees. So that covers the first one. And then it covers the second one because there is actually a displacement and there's no work done. Now, the first example I used, pushing against the wall, I can't use it for that second because, I've used the concept that there's no displacement there. So I have to kind of come up with another example if I wanted to. So, another example is, and I'll give you a hint, is to do with kind of centripetal accelerations and centripetal forces. So if you recall, right, so centripetal forces are actually towards the center, right? So they're center seeking towards, that particular kind of center of whatever turn that you're making. But yet you're not moving towards the center, right? So you're actually moving, as you're going through kind of tangentially, to that rotation. So again, what you're going to run into, you might have a force which is kind of towards the center of the, circle, but yet, you're kind of moving around in this direction. So within here. Okay, so if you notice, these are going to be actually perpendicular to each other. And again, you run into this problem right there, where you're going to have the cos of the angle being basically 0 just by definition. So work, okay, there's going to be no actual work if you are referring to this example. So those are, a few examples that you have, and they really test your understanding. Okay, so what is work all about? So we can do all kinds, right, of pushing, but yet we might not actually do any useful work in here. So those are some examples within here. So that is it for those two examples. So here's another example. Okay, so give an example of where the force and displacement are in opposite directions, resulting in a negative work being done. Okay, so again, if they're in opposite directions, then work, right? So if you have force and then you have displacement, then what that means that the cos of the angle, so right here, if they're in the opposite directions, that means this is cos of 180 degrees, which indeed is -1. And if you take the force and the displacement and you multiply them by -1, so these two are magnitudes in positive direction, then what you're going to get is you're going to get a negative number. Now, what the heck does a negative number actually mean? Well, let's think about that. All right, so with regards to the example, okay, that I can think of, kind of right on the spot. So if you have an object and let's say, it is moving at a certain, maybe velocity, okay, in this direction. Now, if there is friction, so if this is on a surface and there's friction on it, then you know that there's going to be a force of friction, which is going to be in the opposite direction. But of course, okay, so this object might move, okay, a certain amount of distance before it stops, right? So it is moving in this direction, yet the force is in the opposite direction, which is the force of friction. So these two are 180 degrees from each other, right? Which means that you're going to get negative work. So that is an example where this can happen. Now, what does this negative work actually mean? Well, so typically positive work, so remember that work, it's kind of like transfer of energy from one side to another. Okay, so this particular object is actually, it's almost like you can think of it as it's losing energy or it's transferring energy out of the actual system. Now, in this case, it's going to go to the friction, most likely to heat, okay, and it's going to get dissipated. So that negative actually means that it's almost like it's a loss, and a positive typically means that it's some kind of a gain or a transfer of energy towards the object, and negative means away from the object, right? So that's exactly what it means. So that's it for this example. Here's another example. So it says, what is the amount of work done by a nurse pushing a stretcher with a constant net force of 85 newtons that displaces the stretcher by 5.5 meters in the same direction as the force? Okay, so this one is very easy. So if they're in the same direction, then what we would have is that the amount of work is just nothing else but simply the force, okay, that we have multiplied by the displacement in here. So if they're in the same direction exactly, then okay, that cos, okay, angle in between them is 0, so they're in exactly the same direction. So this is just simply nothing else but 85 newtons. Notice that it's in metric standard units already, times 5.5 meters. All right, so here it is. So it's 85 multiplied by 5.5. And that would have been 467.5 Newton meters, okay, or in other words, joules. Now, if we want to round to 3 significant figures in here, then this is going to be 468, joules, okay, of work that has actually been done. That's it. That is all for this particular example. Here's a neat example. So this kind of forces you back into joules, and again, getting more comfortable and going back and forth and seeing various units for work or energy. So here it's joules, and wants us to convert to millijoules, to kilojoules, and to calories, right? So these are actually calories right there, where they give us what the conversion ratio in between them is. All right, so this is a capital calorie. Now, by the way, so this is just for your own sake in terms of understanding, a small little calorie, so be careful, because a small little calorie is 4.184 joules. Notice that a small calorie is basically 1,000th, okay, of the big calorie. So when we do write a capital calorie, really what we mean is kilocalorie. That's what we are referring to. Okay, so there is a distinction between a capital C and a small c. So that's something that you should be aware of. Now, if we're going to be converting this, so this is 2.5 times 10 to the 6 joules. Sure, you can certainly write this out, within here. If you wanted to put it back in, kind of into a whole number, so that's exactly what it is. Sometimes it's easier to be able to go back and forth between here. So if you want millijoules, well, so millijoules, okay, is going to shift the decimal over, 3 places to the right. So that is going to be quite a big number right here. So 1, 2, 3 millijoules, or you can write this as 2.5 times 10 to the 9, okay, millijoules. So if you wanted to write it in scientific notation, so that's that. And now if you want it in kilojoules, well, kilojoules is going to move the decimal over on the opposite side. So for kilojoules, this is going to be 2500 kilojoules, or again, you can write it in scientific notation. So that's going to be 10 to the 3 kilojoules. So that's that. And then finally, your calories. Well, so if you wanted to do your calories, you can take the number right there, and then you can multiply it. So do the regular standard unit conversion. So 4184, this is joules, this is 1 calorie. And you can take out your calculator. And let's see what it gives us. So this is going to be 2.5 times 10, okay, to the 6. All right, and then this is going to be, I guess, divided by 4184. And there we have it. So this is going to be 598. I'll leave it to 3 significant figures there for you. All right, so there you have it. That would have been the conversion for this example. That's it. That's all you have. Here's the last example for this particular video. So we have an object and it experiences a constant net force, and this net force is 25 newtons to the right. Now initially the object is moving at a speed of 1.8 meters per second if the force is present for 2.5 seconds, and the object has a mass of 25 kilograms, then what amount of work has been done on the object? All right, so that's what we want to be able to find out. So there's quite a bit of information in here. So let's take a look. So what is given? I'm going to write all of these things down so that I just kind of have it there for me. So F, so we have the net force, so that's 25 newtons. This is to the right. I'll put it in this way. We have an actual speed, so we're going to assume that it's in the same direction. This is, let's say, the initial speed, which is 1.8 meters per second. So everything is in SI units. The total time is 2.5 seconds, and the object has a mass, all right, so this is going to be a mass of 25 kilograms. Okay, so let's take a look. Now, what do we need? Now, in this case, they're all in kind of the same direction, right? So in terms of F net, so it's going to be in the direction of the movement. Now, because you have an F net, okay, so that means, okay, it looks like, we're going to be, accelerating, okay, at this particular rate. So let's take a look. Work is equal to, so in this case, it's going to be the force. I'll just write force F net multiplied by the displacement itself. All right, so that's what we have there. And now let's take a look. All right, so we have this already. We're going to need to try to figure out this. Okay, so in that case, our displacement is equal to, now there's obviously many equations that we can use in here for displacement. Now, one of the nice things is because we have F net and we have the total mass, we know that F net is equal to mass times acceleration. So I can actually obtain what the acceleration is in here in order to do this. So this is going to be 25 newtons. This is 25 kilograms. All right, so this one's very easy. If you divide both sides by 25, you're just going to get 1 meter per second squared. That's my acceleration. So therefore, I can get my displacement now. So my displacement is, so I'm going to just use my standard equation. So VI, right, so times delta t plus 1/2 times the acceleration and delta t squared. So let's substitute all of these in here. So 1.8, this is all in metric standard units. So this makes it very easy. This is 1 and this is 2.5 squared. So let's see what that gives me. Let's plug it all in. 1.8 times 2.5 plus, and I'll put all of this in brackets in here. So 1/2 times 1. Okay, so that one is easy, times 2.5 and 2.5 squared. All right, so let's take a look. Let's hit that. So that would have been 7.625 meters. So if you need work, well, you can take your F net, which is 25 newtons. You can now multiply it by the displacement. So displacement I already have on the calculator. So I'm just going to multiply it by 25. And that's exactly what we would get. So the work is equal to 191 joules if you round to 3 significant figures. All right, that is it. Thanks for watching. See you in a future video. Bye, everybody.